tilted in random directions. Likewise, the orbital planes of the planets, they're also tilted in random directions relative to our line of sight. I'm going to show you an animation of what this might look like in our galaxy. In this animation, we're going to see the edge-on systems, which are the ones that we're trying to find. That's the first system that we see. Here we're going to see the planet transit and cause that telltale dimming. But some systems are actually going to be inclined 90 degrees relative to your line of sight, with none of the planets ever transiting. But most stars are going to have some kind of an intermediate inclination. Here we have a system that's inclined, and it's inclined enough so that none of the stars ever transit. Here also we find nothing. And in the final system we're going to show it's inclined just slightly enough so that the inner planets transit. We will detect those, but we'll have to detect the outer planets with other techniques. They won't be transiting. So it's a numbers game, really. I mean, we need to observe lots and lots of stars because the probability of that geometric alignment is very small. It's something like 1 to 10%. So we're going to accomplish that in two ways. We're going to look at a very large field of view. Our telescope's going to capture a large piece of the sky, lots of stars. And we're going to point the telescope to a place, hopefully, where there's a high concentration of stars. So in the next graphic, if we were just to take a picture of the night sky far away from city lights, it might look something like this. The Milky Way arcs overhead, and it's here where the density of stars is highest. And you can see in the graphic the stick figure showing the constellation of Cygnus, right smack in the middle of the plane of the Milky Way galaxy. So we're going to zoom in on Cygnus in the next graphic. You can see that our field of view is nestled under the wing of Cygnus the Swan, right between the bright stars of Vega and Deneb. If I can have the next graphic, please. Okay. So we've got this field of view that's nestled underneath the wing of Cygnus the Swan, right between the bright stars of Vega and Deneb. These are very well-known stars in our summer sky. The size of the field of view, you heard, it's about the size of your hand if you were to hold it up at arm's length. And that might not seem to be very big, but let's put it into perspective. A full moon in the sky is only about the width, maybe half of your pinky finger. If you hold it up, that's about the size of the full moon in the sky. The Hubble Space Telescope looks at an area of the sky that's something like the size of the pupil of George Washington's eye on a quarter. It's very, very tiny. So this field of view is 100 square degrees. It's quite large in comparison. Again, we want to catch a lot of stars. So in the next graphic, we're going to look and see where this field of view, the context, the three-dimensional context of our galaxy, where it fits in. So here's an artist's rendering of the Milky Way galaxy, and the yellow cone shows you the area of space that Kepler is going to target. And so we're looking at a region of space in between the spiral arms, in between the Sagittarius and Perseus spiral arms of our galaxy. We've got some stars that are as close as some tens of light years, but the majority of them will be hundreds, even up to a few thousand light years away. Even so, we're still looking at the solar neighborhood, really. Our galaxy is 100,000 light years in diameter. We're looking at stars that are bright enough so that our ground-based telescopes can get very good follow-up observations on them. So in this yellow cone projected onto our camera, we're going to see something like 4.5 million stars. And they're going to be spread over 95 million pixels. But the thing is, not all of them are interesting to us. We can actually save a lot of time and money if we cherry pick those stars that are going to be capable of yielding the detection of a habitable Earth-like planet. And that's what we want to do. We want to cherry pick the ones that are of most interest to us and will give us the highest scientific yield. The next graphic shows a depiction of the types of stars we are targeting. You can see that they come in all different colors, masses, sizes. But the stars that are going clockwise from the top down to the right, down to the bottom, those are the really typical run-of-the-mill, middle-aged stars in our galaxy, and those are the ones that we want to target. Our sun is in the middle of that distribution, so some of them are bigger, more massive than our sun, hotter than our sun. Some of them are smaller, less massive, and cooler. And the star on the left is labeled an evolved star. This is really the biggest star that we're going to observe in our sample. As stars age, as they enter their old age, they become bloated, they puff out, they begin to burn more furiously in their core, and that causes their radii to grow significantly. And it can grow so much, it can be 100 to even 1,000 times larger than the sun. And in doing so, would incinerate any habitable planets like the Earth that happen to be in its way. So we want to avoid those stars, and they actually comprise something like 50% of the stars in our field of view. In fact, there are only about 300,000 stars that are really ideal for detecting habitable Earth-like planets, and those are the ones we want to find in this sea of 4.5 million stars. So how do we do that? Well, we've spent the last 5 years using ground-based telescopes to observe the entire Kepler field of view. And our ground-based telescopes had to make 1,600 pointings just to cover this whole entire field. And what they did was they determined the brightness of all of these stars, the surface temperature, and the surface gravity. And those three things combined give us enough information to decide which are these typical middle-aged stars, which are the ones that are slightly evolved but not so big that they would have incinerated their habitable planets. So we've carefully chosen the field of view. We have cherry-picked the best stars, and we've done this to really optimize our science yield. And now we're just really excited to get started.
Thank you, Natalie. And now to co-investigator Dr. Gibor Basri from the University of California at Berkeley. Dr. Basri.
Thank you, George. I'd like to talk a little bit more about the habitability of planets and also about the stars that they're orbiting. The primary question that Kepler's interested in is, what is the frequency of terrestrial planets in our galaxy? As other people have said, we know something about how many giant planets there are out there, but we actually know almost nothing about how many rocky planets there are. So that's the primary question, and we would like very much also to know about the stars around which those rocky planets orbit. The question of habitability draws on a lot of factors. Some of them have to do with the planet, and some of them have to do with the star. So we know how luminous these stars are, so that we can tell, and we can tell what the distance of the planet from each of those stars is. So we can kind of calculate the average surface temperature. If I could get the first graphic, as Natalie mentioned, we're looking at a bunch of different kinds of stars. So some of them are hotter and brighter than our sun, some of them are cooler and fainter than our sun. So where the habitable zone is depends on what kind of star you're looking at. For the hot stars, the habitable zone has to be further away from the star than our suns, and it's also larger than our suns. For cool stars, faint stars, which happen to be the most common kinds of stars in our galaxy, you have to really huddle in close to the star to get warm enough to have liquid water on your surface. If our sun were replaced by one of these common stars, the Earth would need to be well inside the orbit of Mercury in order to be a habitable planet. That's actually good because Kepler is more sensitive to planets that are close into their stars. So for those small stars, the habitable planets will be close in, so they'll have short orbital periods, so we'll be able to see the three transits sooner. And the star itself is also smaller, so an Earth-sized planet blocking out a smaller star will make a deeper transit. So both of those make the small stars actually favorable for perhaps the first discoveries of terrestrial planets around other stars in the habitable zone. But it won't be stars like our sun to begin with. So as Bill said, we'll have to wait for the answer longer to find out about sun-like stars, but maybe we'll find out something about planets around very small stars first. If you're on one of those planets, of course, it's not just good enough to be the right distance from the sun or the star. You need to have the right kind of atmosphere. You need to have an atmosphere in the first place. Kepler's not going to find out about the atmospheres or whether there's actually water on these planets. So it's really an assay of what the real estate market is out there for rocky planets, but it won't actually tell us how nice the homes are. That we'll have to wait for other experiments. We're also, of course, as I said, interested in the planet's stars, and we can learn some other things relevant to habitability. So, for example, stars are all magnetically active. And if I could have the next picture, this is next movie. This is a movie of our own sun. This is taken in high energy light by the SOHO spacecraft. So it's